perspective, the biggest threat of a steam trap being failed is when it's failed in the open position. And when a steam trap's failed in the open position, we've got that steam that basically passes across the orifice, and it is going to find its way to a vent. Now, typically those vents are going to be sited on the top of condensate receivers. So if we've got that live steam being vented away to atmosphere, obviously it's a huge loss of energy. So if we know the size of the steam trap and therefore the size of the hole in the trap itself, if we know the steam distribution pressure, if we know the operational hours per year, then we're able to determine the loss of energy that is going to reflect to the steam using client. So if you consider a failure rate of 1 in 10 seems to be the average. If a client's got 1,000 traps or even 100 traps on site, a failure rate of 1 in 10 can represent a significant loss of energy over a financial year. And if our client knows their cost of steam, well, the calculation's an easy one. So it's highly encouraged that steam using sites undertake a periodic audit. Now that could be a manual audit that is undertaken typically once a year. The steam trap will be checked for operation, open or closed. It will be checked to see if it's the right type of trap or if it's been sized or installed correctly. If it hasn't, well, the appropriate modifications can be made and we can enjoy a significant payback. Or in more sophisticated processes, the trap operation can be monitored automatically in real time, where a reading can be relayed automatically to a BMS or even to a computer or even a mobile phone to advise when a trap's being left in the open position or closed position, so the maintenance team or production team can take the appropriate steps. With regards to utilizing the steam efficiently, we know that there's still a lot of steam using sites out there that are using shell and tube heat exchangers to generate sources of hot water for process purposes, rather than the modern, efficient, instantaneous plate heat exchanger. And because an instantaneous plate heat exchanger has got a far bigger and more efficient heat transfer surface area, we don't need to hold any water in the secondary side, hold water in storage. So that smaller heat exchanger means that we've got less water held in storage, so we've got less irradiating loss, less standing loss. And it also means that we've got a significant reduction of footprint that can result in smaller plant rooms. It also means we've got a much greatly reduced mass of metal in the solution itself, meaning those radiating losses are reduced further still. There are obviously additional benefits that aren't necessarily representative of energy efficiency cost savings, such as a reduction of plant room space, a reduction of maintenance costs, a reduction of Legionella risks and so forth. But of course, they can't really be attributed to energy cost savings. So we've also spoken previously about the benefit of condensate. Condensate, it's hot water. But remember, we know that water's got a specific heat capacity of 4.19. And after all, condensate is water. So condensate exists whenever steam gives up its heat energy. That can be in the distribution pipework, and it can also be at the process. Now, condensate can cause a number of problems if it's left in the distribution steam pipework. Not only can we get that erosion, corrosion, and water hammer we've spoken about, but it can ultimately degrade the steam and reduce the energy value of the steam as it finds to the process. And if condensate's left at the process, it can back up and flood the steam space. So we know that we need to remove the condensate and take it away from the network, but we also know that it does have a value if we can return it back to the hot well. Remember, condensate is water. Water's got a specific heat capacity of 4.19. Therefore, if the condensate exists at 0 bar gauge, at 0 bar gauge, we know that water and steam have got a similar temperature. 100 degrees C. So if we multiply 100 by that 4.19, that tells us that every kilogram of condensate has got 419 kilojoules of energy contained within it. If we can return that to the boiler house, well, it's 419 kilojoules of energy that we're potentially saving if we were bringing the water up from 0 bar gauge to start, from 0 degrees to start producing steam again. So one of the things that really causes a lot of problems on our client's site is the overlook the value of condensate. They underestimate the true value of that condensate. And that's because they may not be handling it correctly, or they may not be giving it the due respect it deserves. So this little graphic that we've gone through previously hopefully will emphasize the benefit that condensate has. If we've got a steam process that is condensing steam at a high pressure because it requires that high temperature, the example we've got here, 7 bar gauge, where we know that steam exists at 170 C. When steam gives up its energy and condenses, that condensate is now a liquid. It's given up its latent heat. It retains the sensible heat. But the temperature of the condensate at 7 bar gauge is 170 degrees, the same as steam. At this point here, the condensate's under pressure. It's the same pressure as the process. At 7 bar gauge, the sensible heat in the condensate is 721 kilojoules. Now there needs to be a fall in pressure downstream of the steam trap, otherwise the condensate wouldn't move. And in the example of a fall in pressure to 0 bar gauge, well, the steam tables tell us that at 0 bar gauge, the condensate can now only hold 419 kilojoules of energy. So what happens as we get the fall in pressure? Well, that condensate, it needs to give up that excess energy very, very quickly. The only way that excess energy can be given up is by a certain percentage or a certain mass of that condensate changing state to flash steam. So there's a change from sensible heat back to total heat again. The problem is we get a huge expansion of volume. And that's what catches a lot of steam using sites out, because the best way to deal with that expansion of volume, so they believe, is to vent it away to atmosphere. Once we've vented that expansion away to atmosphere, we can now pump the condensate back as a liquid all the way back to the boiler house. And if we're pumping it back as a liquid, we're not at risk of cavitation, and we're not at risk of having to do so in a very large size pipe diameter. Because if we're pumping a liquid, that flash steam's gone. And yes, that certainly is the case. But by losing that flash steam, we're losing a significant amount of energy that could potentially be used elsewhere. So we've previously discussed condensate management in quite some detail. We know that condensate, in many cases, it's got to be pumped back if it exists at a low pressure. So we've got to protect those electrical pumps. We've got to let the condensate fall to 0 bar gauge to avoid pump cavitation. So that flash steam's got to be vented away. And we also know that if we know what the pressure drop is, we can calculate how much condensate as a percentage is going to change state to flash steam. So we can calculate its financial value, and we can calculate if or where that condensate can be reused elsewhere in the plant. And if we can't reuse that flash steam elsewhere, then maybe we can condense as much of it as we can and return that liquid condensate back to the pump, thereby increasing the condensate rate. And we also, if we know the mass flow of condensate that we can now increase and get back to the boiler house, then if we know the cost of steam, the cost of water, the cost of fuel and chemicals, then we can demonstrate an attractive payback for our clients. Condensate, it is one of the biggest areas where we can help steam using sites to enjoy cost saving benefits, reduce their energy consumption. We also know that certain processes, they can be working in areas that can be hazardous, By hazardous, I mean in terms of contaminating the condensate. For example, anywhere that is encountering acids or oils or fats, for example, getting that back to the boiler can have a catastrophic effect on the steam boiler itself. And it also means that the acids and the fats can be carried from the boiler in the steam and potentially cross-contaminate another process. So a lot of clients are still dumping condensate to waste to protect the process, and that's absolutely the right thing to do, but only when there is a risk of contamination. So we've spoken previously about how we can detect contaminated condensate, and we can do that by using either a turbidity probe or a conductivity probe. So that will identify very, very quickly when there's a problem with the condensate. So if there's a risk of contamination, the probe will send a signal to a diverting valve and it can be dumped. So it means for the majority of the time, we can recover the condensate and enjoy those cost savings. And contamination control devices can either be mounted in line, or for larger solutions, they can be skid mounted. I suppose even when that condensate is being dumped to waste, then there's no reason why we can't take the energy from it and add it back to another process. So we also discussed blowdown in, I think it was our very first presentation. So both TDS, which stands for total dissolved solids, and the bottom blowdown, well, it needs to be performed because it helps us to maintain the boiler water chemistry. And I think the analogy that I often use is if we've got a cup of tea and we add a spoon of sugar and then a spoon of sand into that cup, well, the sand, that's going to fall to the bottom of the cup. The sugar will dissolve. Keep adding sugar, keep adding sand, and we know that over time the sand is going to occupy a lot of the volume within the cup, but the sugar will continue to dissolve. And that's kind of the same as what's happening with the minerals and chemicals that are present in the raw water and that are being added into the boiler. So as water is being evaporated and steam's being produced, we find that the chemicals that are held in suspension, the TDS, the sugar in our analogy, it gets more and more concentrated. It's going to produce foaming. So we know that we need to perform bottom blowdown daily, and we also need to perform TDS blowdown at the side of the boiler periodically to protect that foaming effect that we've spoken about previously, which can result in wet steam and a lot of scale and carryover. Now, traditionally, blowdown's been performed manually. The problem with manual blowdown is it's nigh on impossible to state exactly how much water is being taken out of the boiler. And there's a tendency to overestimate, which can result in a huge energy loss. Or if we underestimate, then that's going to have an impact upon the steam quality and the safe operation of the boiler. So the good news is if we can recognize a manual blowdown valve, whether it be bottom blowdown or TDS, and encourage the steam user to move towards an automated blowdown control, then we can, in many cases, represent a significant payback. Now, boiler manufacturers, they will determine in their OEMs exactly how much blowdown should be performed. So we can quantify very, very easily if and when we know that an over blowdown is being performed. We can determine what the energy loss is, and we can determine what the cost saving would be by moving from manual controls towards automated controls. And in many cases, we can be talking about a payback within months, if not, well, certainly sub 12 months. But that blowdown still needs to go to waste. It's nasty stuff. We can't use it anywhere else in the process. But as with other areas of site, there's no reason why we can't utilize the flash steam that is produced whenever we get a fall in pressure from the blowdown water, the flash steam, and therefore that total heat energy. It will be clean. It won't have any of the particulate in it, so we can reuse it. And the residual blowdown can go to waste, perhaps being put through a basic heat exchanger where we can use that heat energy to add some temperature to the incoming makeup water, thereby helping us to keep the hot well at a target temperature that's nice and high. Again, a very, very good area that we can retrofit a solution to bring around an attractive payback. But there are always going to be certain areas where we know that we're going to have a lot of flash steam, and that's down to the mass flow of condensate and the high pressures that we may be using that condensate or maybe using that steam at. So we know that flash steam needs to be vented to protect condensate pumps and pipes from overpressure. So for smaller volumes, we can use that flash vessel that we've spoken about on the previous slide. But for larger volumes of flash, we can really use what we refer to as a flash recovery energy management skid here. And that really uses both the flash steam and the condensate in different phases. We can pass it across a very simple heat exchanger to add energy to another process. The key here is recognizing a process where a significant amount of flash steam is likely to be produced. So I'm thinking about laundries, the textile industry, distilleries. By no means a limited number of processes, but wherever we've got a high steam consumption pressure, that's where we expect a significant pressure drop to result in a lot of flash steam on the condensate line. And a significant payback can be enjoyed under these circumstances. Now, we also know that metering the steam, both in the boiler house and at the process, is critically important. It can help us understand the overall efficiency, not just in the boiler house, but also at the process as well. The key thing is understanding that we need to select the correct type of steam meter to match the process. As with steam traps, there's no such thing as a universal steam meter. They all operate in different ways. But I think the key things to bear in mind are phrases that we use, such as turn down. And that's essentially the difference between the highest and the lowest loads that the meter will need to read. We've got the accuracy, and that's the ability of the meter to take a true and correct value. And we've got the repeatability, and that's the ability of the meter to read the same value twice. So that could be an incorrect or an inaccurate reading, but it's the ability to take the same reading on more than one occasion. So with regards to accuracy, it's important to understand that different manufacturers will quote accuracy in different ways, and this can be really misleading. So first of all, let's look at full-scale deflection. Well, if a flow meter can pass 1,000 kilograms per hour of steam at a 100% capacity, a full load, and if it's been quoted as having a 3% full-scale deflection accuracy, that means that there could be 30 kilograms of steam that is not being read by the meter. But then if the process falls to a low load, say 100 kilograms per hour, then it means that the meter is still failing to measure that 30 kilograms per hour. So what was a 3% inaccuracy at a full load, it extends to become a 30% inaccuracy at a lower load. So it's therefore far better to have an understanding of what we call an indicated flow accuracy. That basically means the percentage accuracy or certainty. It means it's going to remain the same regardless of the flow rate we're looking at. And we also know that when we're looking at steam meters, we need to observe good working practice when it comes to ensuring that the steam meter is fit correctly. It's not a single item. It needs to be fit in conjunction with the conditioning ancillaries. For example, we've got the separator here and we've got the strainer. The strainer and the separator, they protect the flow meter from any debris or any effects of erosion. And also an excess of moisture present in the steam means that the steam isn't going to have the mass flow rate that it was expecting. So we need to take any entrained moisture away across a steam trap. We need to vent any air away for similar reasons. We need to ensure that we've got laminar flow, so we've got the correct run of pipe upstream and downstream of the meter. We want to fit a check valve to prevent any condensate from being drawn back across the meter, which could cause damage and water hammer. So quite often we'll go to a site that's using steam. We'll ask them if they're metering the steam. They'll say, yes, we're metering steam, but we'll find out for whatever reason, either the steam isn't operating accurately for reasons we've already mentioned, or that it's been proved to be faulty because it hasn't been installed correctly. So we know the value of metering steam. We also know that certain processes, especially in building service applications such as hospitals and universities, we know that they're going to follow building regulation CIBSE Part L that determines that if they're interfacing with an existing or a heat exchanger that hasn't had some attention in some time, we know that we're obliged to follow good practice and ensure that it works efficiently. And the only way we can do that is by ensuring that whenever we are undertaking any remedial works, we do fit a steam meter to prove that it is working efficiently, or if it's working inefficiently, we're at least aware of the extent of which it is doing so. So on the subject of meters, another way that we can help to understand the overall efficiency of the wider steam and condensate loop, it's by fitting an energy console in the boiler house. And that console can take an input from any number of meters around the energy center. For example, if we're metering the water coming into the building, if we're metering the fuel coming into the boiler, the water leaving the feed tank and going into the boiler, and the steam that's leaving the boiler, well, we can take an input from all of those meters. So let's say, for example, if over a period of time, we found that the steam flow rate had remained consistent, as had the amount of water that was being consumed from the feed tank. But the amount of water that we were taking from the mains had shot up. And imagine we identified we were using more and more fuel. Well, the console would tell us in real time. It could send an alarm, send a reading to quantify these costs in financial terms. And we may then decide to walk the plant and identify what's gone wrong with the distribution network. And for the vast majority of cases, it will be down to the fact that we're simply not recovering as much condensate. Remember, if we're failing to recover that condensate, and it could be for reasons of failed or cavitated condensate pumps, condensate being dumped to waste for fear of contamination, it could be failed steam traps or flash steam vents, both of which means that we're reducing the amount of condensate that could be returned. If that were to happen, we'd need to replace that condensate with more water coming from the mains, and we need to bring that water up to temperature again. So we can make sense of all of that to identify the financial implication and where that inefficiency was being caused in the first place. Now we can take that one step further, because all of our area engineers, they've all got detailed software on site. So if we know a few key parameters on a steam using site, for example, it could be the cost of water, the cost of water treatment chemicals, the cost of gas, all of which should be readily available, together with the steaming hours, then we can determine all of the variables that you can see on the screen. We can determine the financial value of condensate. We can tell them how much condensate is being recovered. We can then compare that to how much should be recovered and identify white space for cost-saving analysis. If we can identify where steam traps have failed, how much flash steam is being lost, then we can roll that up into a bigger picture, and we can generate a roadmap where our steam using sites and clients can very, very easily identify where cost savings can be made, and they can prioritize the projects that they should be identifying moving forwards. So just to leave you on something that has become quite topical over recent years, and that's the old CHP argument. And we know the benefits of moving away from a traditional or conventional form of generation for both thermal and electrical energy. And we know the benefits of bringing that together in a CHP system, far, far more efficient when we've balanced it correctly. That's the key word there, balancing it correctly and ensuring that you've consolidated those seasonal variations. But we also know that a CHP engine gives off a lot of energy. It radiates a lot of energy from the shell of the boiler itself that needs cooling. And we also know that there's a lot of energy lost up the exhaust. And there's no reason why we can't recover some of that energy and add that to a steam boiler. So a CHP system is efficient, but if we've got a client that has got a steam requirement, then there's no reason that that cannot be combined to become a modern, efficient, combined steam, heat and power solution. So that brings us to the end of today's presentation. Hopefully it's given you food for thought with regards to where we can optimize an existing or a traditional steam using network, where we can help bring around significant cost savings. To any of you out there that are steam users, please give thought to how Spirax-Sarco may be able to assist you moving forwards. All of our engineers offer a no cost, no obligation walk the plant, where they're happy to give a high level overview where cost savings can potentially be made, give you an understanding of if there's likely to be an attractive payback that could justify a project moving forwards. So moving forwards on the topic of energy and steam, we've very kindly been invited to present an 8th and final CPD presentation in 2 weeks' time on steam, what the future holds. So today we've spoken about optimizing an existing or a traditional steam network. But of course, we want to know what a steam network is likely to look like in 10, 15 years' time. And this presentation will give you an idea with regards to what's coming up in the elevator and how we're working to address the challenges of tomorrow. So thank you once again for bearing with me. You can see details of our training courses online. If any of you do have an appetite for moving forwards with your steam journey, I will make a PDF of the slide pack and of the attendance certificate available to you. If you can make yourselves known to me, drop me an email, send me a message on LinkedIn. I'll get that arranged for you. Equally, if you've got any questions, then if you haven't already dropped them into the chat function, please feel free to get in touch with me. So I'd like to thank Brian once again for arranging today's CPD presentation along with his colleagues at Projects, and I'd like to thank the wider IMechE community as well. Thank you very much. Any questions, Brian? Any questions, Brian?
Hi, Dan. Sorry, minor technical problem there, getting everything switched on.
No problem. I've just been talking to myself for the last hour. So.
Yeah, well, I was saying to myself, as it happens, you knocked it out of the park as usual. Quality job. We had 52 online, so a few more than recent. Yeah, and we've got some very positive comments about your presentation being a downside more interesting than my thermodynamics lectures. Well, I'll vote for that one as well. It is very much more interesting.
Well, put my name forward to your head of faculty, and I'll be glad to help out.
Yeah. So still quiet on the question front. Can only be that you've done a great job and answered all the questions. So we'll just give it a couple of minutes. I'm looking forward to the what the future holds as well. So hopefully that'll be exciting. As I think we're all questioned out here. So
well, we'll certainly do our best. And like I say, if anyone does want to contact me for any more further information, or just for a PDF of the slide pack or a certificate, then please feel free to get in touch with me, and look forward to speaking to everybody in 2 weeks' time.
Okay, that's great. So thanks, Dan. Thanks to Nikki Baxter from the IMechE for doing the back office stuff. Thanks to Jamie Ashton, who's the MD of Project Solutions, who supports me in putting these on. And thanks for everybody for connecting in. Last one in a fortnight's time. Looking forward to it. Have a nice evening. Good night.
Great. Thank you. Thanks. Good night.